Hey, howdy everyone. I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin. And continuing on with my course on subsurface machine learning, we have previously discussed many of the concepts that are required as prerequisites before we do machine learning, things like feature engineering, probability theory, and so forth. Now what we'll do, and we've talked about some inferential methods, we've just started into predictive methods, covered linear regression, talked about ridge regression. I'll do a little bit of recap of that. And we'll dive in today to the LASSO, or is it the LASSO? Well, let's talk about that. Okay, so let's go ahead and dive into the concept of something, LASSO regression. So what's the motivation? Why cover this topic anyway? Well, first of all, we still want to cover methodologies that are simple and have high degree of interpretability. It builds on linear and ridge regression. It has a linkage, once again, just like ridge regression, to variance and bias trade-off, which is super helpful. And we want to enforce the concept of hyperparameter tuning. That's essential. We want to also have a chance to talk about feature selection while performing prediction. And that's super interesting. That's a useful thing. So let's cover LASSO regression. So let's go back and just recap linear regression. Remember, our linear regression model was quite simple. It is, we will take a linear combination of our predictor features, X alphas, going from 1 through M predictor features. We have the parameters we're working with are the B alphas, 1 through M, plus an intercept term. And we're going to predict our response feature. Now, we're going to do this under the constraint of an L2 normalization. In other words, we're going to look at the sum of the squares of the error at all the training data locations, training data I, 1 through N training data. And this is the model right here, just shown right there. So this is going to be our prediction. And so we're going to get the sum of these squared errors. Okay, so residual sum of squared errors is what we're going to minimize. That's what we do with the linear regression model. Now, people may suggest, and this is kind of funny because linear regression model is quite simple. We don't usually think of it being very sensitive. But in fact, for some classes of problems, it may be considered too sensitive. And this is usually when we have sparse data sets that have high variance. For a single training set, there's only one possible linear regression representation. So we want to have a methodology that allows us some opportunity to fit, or I should say, tune a hyperparameter to have some choice about model complexity or control on model variance. And so that motivates us to move towards the ridge regression. And ridge regression adds a new term. It's a regularization term. We know it as the shrinkage penalty, which basically says, go ahead and we want to fit or minimize the squared error at the training data locations, but we'll put a penalty on the size of the parameters. In other words, we want to encourage the model, our machine, to have parameter magnitudes that are closer to 0, that are smaller. And so we'll have a lambda hyperparameter that's going to determine how important that is relative to the problem of minimizing the residual sum of squares of the error. So this is known as the shrinkage method. And what's the impact of it? Well, we can look at it graphically. It's going to create increased model bias. We can see that graphically. Regular linear regression in trying to maximize the fit or minimize the error at the training data locations could be shown as the blue line right here. The ridge regression approach is going to result in a model that is not optimum. In other words, it does increase the bias. We could see this difference between the models would be increased bias. But what do we gain? Well, we gain something really important. We're going to find out as we go along this course that in fact, model variance is huge. And many things that we do to try to improve accuracy are all about decreasing model variance. And so what this does is, you can imagine if I was to do a bootstrap of multiple realizations of the training data, that I would get multiple models, that they would have different slopes. The parameters that are trained for each of the data sets would vary. And because of the fact that we're working with L2 normalization, we might see quite a bit of fluctuation, even with this very simple model. But by putting in this regularization term, what will happen is we will in fact dampen that sensitivity to the actual training data and therefore decrease the model variance. Now what we hope with the model variance and bias trade-off is in fact what we're going to do is we're going to, while we may in fact lose from the perspective of increasing model bias, in fact we'll be moving this direction as we increase our lambda parameter, we'll increase model bias, but we hope the decrease in model variance is sufficient to offset that loss, and the result is that we hope that we end up to decrease the overall expected test mean squared error. In fact, what I should say is improve the performance in making predictions at unseen locations. In other words, in the real world use of the model. Now, so given we've done a little bit of a recap on the regression, linear regression, on the ridge regression approach using a shrinkage term to try to decrease model variance, improve accuracy, the model bias and variance trade-off. Now let's go ahead and talk about LASSO. Okay, so now why am I a little bit hesitant about pronouncing it? Because I'm Canadian, and Canadians sometimes struggle with how to pronounce things because we're kind of a little bit British and we're kind of a little bit American. And so I wondered when I started to use this term in my class why I was struggling with it. And I realized it's because of my background. The American pronunciation is LASSO. LASSO. The British pronunciation is LASSO. LASSO. So you decide how to pronounce it. I'm going to call it LASSO from now on because of my Canadian heritage. Anyway, my mom was British too, so, I guess that makes me British. So LASSO is actually an acronym, and that's why most of the time in the notes I'm using capital letters. It means least absolute shrinkage and selection operator. I think they kind of reach for that one, but that's okay. I get it. It's a regression analysis method that performs, this is the super cool thing, and this is the first time we're going to show a prediction method that does this. Not only regularization to try to dampen model variance, but also variable selection at the same time. And I'm going to show you how it does that. That's super cool. Now, it's all about getting enhanced model accuracy. We know that. We need to improve that model accuracy, but the feature selection actually provides us with a really cool opportunity for improved interpretability. So what are we going to do? How do we get a different method? We're going to build off of ridge regression, and with LASSO regression, what we're going to do is we're going to just simply change the shrinkage penalty, not to use an L2 norm, this square, but to use an L1. So remember with shrinkage, what we had was this squaring. So we have lambda multiplied by the weighting, the sum of the squares of the coefficients. Instead, what we'll do is we'll do the lambda times the sum of the absolute values of the coefficients. So this is the only difference here, is that squared term going to absolute, and that's how we get the LASSO approach. Okay, so now once again, just recall just the difference between the L1 and L2 norm. The L2 norm was known as a Euclidean distance or Euclidean norm, and it's all based on the square. And if you were to replace the deltas in each one of the features or the coefficients with an x and y delta, this would be a measure of regular Euclidean distance. And we have a generalized p norm that we could be working with. Now what we're going to do is we're going to go ahead and just work with p equal to 1, which is the L1. Now what's the difference? Just to recap on this, the difference between the L1 and the L2 norm. With the L1 norm, we get a solution that is more robust, in other words, more resistant to outliers, but it is more unstable. It will tend to have jumps as we change the lambda parameter or the training data. Now, there were the other concepts that I mentioned before. I won't recap all of those right now, but that's sufficient right now for our discussion. Go back to lecture 9 if you want to hear more about norms. I have a recorded lecture just about norms. Check that out. Okay, so robustness, stability. The robustness is defined as the insensitivity to outliers in the data. L1 is better. And we can safely be less concerned about outliers. L2 is better if the outliers are important. In other words, if we actually feel that the outliers are meaningful, we don't necessarily want to dampen them. Just like in the case of working with the Pearson product moment correlation coefficient versus the Spearman rank correlation coefficient, if the outliers are meaningful, we don't want to dampen that information, right? We just might be sweeping something under the rug. Stability in solutions, L1 for a small horizontal change in the data, can in fact have a massive jump in the model solution. The slope may just switch. And so there's like these tipping points and the model will just change. Okay, so what causes that? Like, how would we explain that? And this is one of the best figures I found looking around the internet in order to explain this idea. I just noticed that I'd forgotten to put the citation to the website. So appreciation to the blog post that's available at this address where I had adapted this figure from. I took their figure and just redrew something a little less complicated that would fit on my slide here. Okay, so basically what's happening. You can imagine that if I was working in a system where I'm trying to find the shortest path between this point and this point, the L2 solution has only one solution. The straight line would be the solution. But if you look at an L1 solution, the L1 solution is behaving like a city block solution. In other words, as long as it is simply taking the sum of the differences, and if you look at every one of these paths, this is solution number 1, solution number 2, solution number 3, they would all have the same L1 norm. Their distance would all be the same. Okay, so now imagine if I take this training data and I just move it slightly. What could happen is I could have a big jump where suddenly I go from solution 3. If I move just a little bit this way, maybe solution 1 becomes a better solution. Or if I move just a little bit up like this, you can imagine that there would be instabilities. It can jump very quickly between dramatically different solutions. Now, this is a very simplified way of visualizing the problem. Now imagine working in a very high dimensionality under this constraint of city block type of distances. And then you understand how we could end up with instabilities. I'll make a couple of comments right now about analytical solutions, but then I'll speak a little bit later about the idea of training the parameters for this model. The L1 norm does not have an analytical solution because it is non-differentiable. It's a piecewise function. It's including that absolute value. So we'll require some type of numerical solution scheme, an approximation. L2 does have a direct closed form analytical solution, and so we benefit from that. Sparsity is also really interesting when we compare the two methodologies, L1, L2. The sparsity is the property of having coefficients that are either 0 or are not near 0. In other words, if we don't have sparsity, we have a bunch of values that go close to 0 but never really get to 0. And so L1 does remove features. In other words, that as we increase the lambda, it's going to, in fact, shrink feature weights, or I should say the slope parameters, right to 0. They'll go right to 0 and then they zero out, and that feature has no impact on the model. That's where we get into model feature selection while building the model. And that L2 will shrink the coefficients near 0 as lambda increases. But you will still have lower sparsity. Excuse the spelling mistake there. So let's visualize that. Let's see the difference between these norms. And this is a common visualization I found online. I believe James and all in their book, they have this type of display too. And many authors have shown these types of displays. So let's compare the ridge regression, L2, regularization, against the LASSO. So for the same regularization cost, we'll have different shapes in the parameter space. So let's go in B1, B2 parameter space. We're putting constraints in the LASSO that we're setting basically that the absolute value of B1 plus B2 must be less than or equal to S for a specific lambda value. That's effectively what we're doing. Now consider that for the L2 regularization. That's the B1 squared plus the B2 squared less than or equal to S, a constraint, and the result will be a circle solution space. In the case of the LASSO, it's going to be this type of square oriented with the corners on each one of the predictive features. Now imagine that shape in a hyperdimensional space. Now, if this was the least square solution combination of the parameters that we would have found with regular linear regression, if we had a large enough S in both cases, in other words, the lambda parameter was low enough and had enough, too little influence to change us from getting that solution, then we would get that. We would get back to having linear regression. But now what would happen is as we increase the lambda parameter. Well, as we increase the lambda parameter, we can't get to that optimum solution, the least squares fit. And so what will happen is we can imagine we'll start to deviate from that. And we could actually draw these shapes right here, and they would represent iso squared error contours. In other words, we're accepting more error because of the constraint on the parameters, the regularization constraint. And so what will happen is if this is ultimately our constraint, that this is only as far as we can go under the LASSO constraint, you could grow these contours out, keep moving away from the optimum solution, and guess what's going to happen with the LASSO? The very first solution we find is going to hit a corner. With a very high likelihood, it's going to be one of these corners. And if you look at the corner, what it is, it's a solution for which the B1 parameter is zeroed out. And the B2 parameter would have this negative value down here along this axis. Now, if we look at a circle type of solution set to our regularization, what will happen is we're more likely to intersect along one of these arcs here, and we're not going to be zeroing out our individual parameters for our model. So this is interesting. The LASSO is going to zero out our parameters. This is really, really cool. Now imagine that's happening in a hyperdimensional space, and I've drawn it in a very simplified space. Now once again, what's the impact of our regularization? Just like ridge regression, is going to increase the bias. The very best model, the least biased linear model we can work with is the linear regression model because it's going to minimize the error at the training data locations. We're going to introduce new bias because we're in fact going to flatten out our model, decrease the slope terms. And so this is going to be the bias in our model. Now, but what we gain is going to be reduced model variance. And this is super cool. We'll see later on when we get into ensemble methods that all we're doing with putting multiple estimators together is all about trying to attack model variance. That's usually the biggest impact on as far as decreasing our prediction accuracy. And so what we'll gain is you could imagine if we bootstrap the training data and we created multiple models, it's basically a form of bagging with our linear regression model, that we would have, and we'll talk about bagging later, we would have multiple models. They'd all have different slope terms. But if we use regularization, what we're going to do is we're going to decrease the sensitivity of our model to the training data. Therefore, we decrease model variance in the model. Now, once again, we're going to do that with a shrinkage penalty term. We've just already discussed that. We showed that it's going to be a lambda hyperparameter applied to the sum of the absolute values. And just like with ridge regression, if we were to have the lambda term basically decrease until 0, we're at a point where this term just disappears and we effectively we're just going to have regular residual sum of squares in our loss function, and that'll be just regular linear regression. If lambda approaches a very large number, the solution will approach the global mean, because as lambda goes to a very large number, we are shrinking all the model parameters. So these parameters right here go to 0, these parameters go to 0 right here, and the result is that we are left with just minimizing the square difference between the training data and a constant value. And the very best constant value we can come up with to minimize that squared error, in fact, is going to be the mean. And we know in expectation to minimize the squared residual, the best value we use is the mean. Okay, so now I mentioned the fact that this approach has a really cool aspect to it, and that is from the standpoint of feature selection. So let's go back to, let's produce a plot. And what this plot is we're solving a multi-linear regression with ridge regression right here with lambda hyperparameter and with the lasso down here with our lambda hyperparameter. Now notice we've put in here different scales for the lambda parameters. I've used a log scale here, a log scale here, but I use different scales to kind of highlight specific behaviors and forms. And so what we can see in general is that if we use a lambda parameter that's very, very small, we're going to basically have linear regression. There's no real impact of lambda parameter. At some point, we're going to see that we start to impact the parameters of the model and they start to all shrink towards zero. Now notice they all shrink basically together. For the most part, they're all kind of shrinking together towards zero. Now what's really interesting is if we go ahead and we look at the behavior of the lasso, what actually happens is that if we look in detail here, they don't shrink together. What actually is happening here, and if you look here, the lambda parameter we're talking about is 10 to the negative 2. That would be right here on this scale. We can already see that some of the individual parameters are already zeroing out. First of all, acoustic impedance, then total organic carbon, brittleness, log permeability, and finally porosity at the very end. A large enough lambda parameter, once again, we've reached the point where you're just going to estimate the global mean. All the parameters are just zeroing out. So this is really cool. We can see the sequential order over which our individual predictor features are being zeroed out, and we could use that as a scheme given the assumption of a linear model and so forth, all the other assumptions of homoscedasticity and so forth. We could use that as a feature selection method. What's our most important feature? The last one to be zeroed out. The first feature to be zeroed out, acoustic impedance, is the least important feature. And so we can use that. We have the order now. Porosity is most important, then log perm, then brittleness, TOC, and finally acoustic impedance. Now let me just make a couple of comments around the lasso and training the model parameters. I want to reinforce this point. This is important. When we switch to the L1 regularization, once again, we don't have an analytical closed form solution any longer. We showed in the ridge regression lecture that we can actually derive, using matrix math, but we could derive the actual methodology to calculate now there was a matrix inversion, but to calculate the parameters, and we said that we had confidence that in general that matrix would be invertible, and so we'd be able to calculate those parameters using matrix math. Now, we don't have that closed form solution for the lasso, and we're now going to rely on a numerical solution scheme, like gradient descent. We'll talk much more about gradient descent when we get into gradient boosting later on in this course. But there has been a recent paper that demonstrates the lasso solution is unique for any number of features, and for any number of features that actually have weights. P in this case would be features that remain for a lambda value. In other words, haven't been zeroed out. Because remember, this is equivalent to feature selection. So just like we did with dimensionality reduction and feature selection, M was the total number of features, and P were the remaining selected features. In the case of projection, feature projection, there were the number of, say, principal components we worked with. Now, I should comment, this has been shown that's unique for the case in which all features are continuous. If some of your predictor features are categorical, you may lose this attribute. All right, so we will have some hands-on. I have an example in Python for working with the lasso, but this is the end of the lecture right now. So if you want to check that out, that's on GitHub, on my GitHub repository under Python numerical demos. Under Geostats Guy is the name of the account. I hope that this lecture has been useful to you. I really enjoyed covering this topic. I think it's essential that we cover this topic as far as understanding the overall idea of regularization, feature selection, and working with simple, highly interpretable methods, and then building up. All right, so I am Michael Pyrcz. I'm an associate professor at the University of Texas at Austin. I work in data analytics, geostatistics, and machine learning with my group of PhD students. We are the Texas Center for Data Analytics and Geostatistics. I share all of my lectures online on YouTube, and all of my worked out examples are on GitHub, and I share a lot of good information on Twitter. All right, take care, everyone. Bye.